Good evening, all. And
Yes, sir, go ahead.
Yeah.
Good evening, all, and welcome to the fifth session of Institution of Naval Tactics for this year. Today's lecture is special because we have got Professor Ghosh, who is a doyen of our field, the senior most practicing naval tactic probably in India. And we have got a chief guest, Professor Vendhan, who is a veteran, and we all look forward. And Mr. Dasgupta, who will be chairing the session. The topic is also interesting, transitioning to ship structure design by FEA. And it's my privilege to introduce the session chair, who will further introduce Dr. Ghosh and Professor Vendhan formally, because all the three of them need not have any introduction. Mr. Dasgupta, I know him as former president of Institution of Naval Tactics personally, and he has had a very long career in Mazagon Docks. He did BTech in Naval Architecture in Kharagpur and then an MTech in IIT Bombay in Structural Engineering. He had been the chief surveyor in Indian Institute of Shipping and also associate various shipyard, L&T, something which I remember, and other shipyards. Now he's the vice president of Arush Gas Technologies. This is just a formal introduction because I have to introduce him. Otherwise, this forum requires no introduction. Mr. Dasgupta, with this brief introduction, I would like to hand over this session to the session chair, Mr. Dasgupta. Please, sir.
Thank you very much, Dr. Iyengar, and good evening, friends. Today's webinar will include a presentation by Dr. M.K. Ghosh. As Dr. Iyengar has already said, he is the doyen of Indian Naval Architects, and we are honored by the presence of the maritime offshore industry. Considering the importance of this topic, which has been in existence for at least 50 years, I reckon many of the attendees here would be quite conversant with this topic and its applications in ship structures and hydrodynamics. I would expect an involved and interactive session today during the presentation and after the presentation. Let me begin with the introduction of Professor Vendhan. Professor Vendhan, who is the chief guest of this session today, is a rector of IIT Madras, a most eminent academician and scientist in the maritime field. Professor Vendhan did his BE in Civil Engineering and MSc in Engineering in Structural Engineering from College of Engineering, Guindy, University of Madras in 1968, and completed his PhD in Civil Engineering from IIT Kanpur in India in 1975. His professional experience includes from 75 to 1979, he was a postdoctoral research associate of Department of Civil Engineering, University of Massachusetts, Amherst in Massachusetts, USA. Between 1979 to 1980, he was a research associate at the Ocean Engineering Center, IIT Madras, which was known then before it was transferred as a Department of Ocean Engineering. And from 1980 to 2010, he was the faculty of professor and a professor since 1990 of the Ocean Engineering Department of IIT Madras. In 1989, for about 3 months, he was a German academic exchange. He received the German academic exchange scholarship, which is called and was a DAAD scholar, University of Hamburg, Germany. He came back and became the head of Ocean Engineering Department from 1997 to 2000. And from 2010 to 2015, he has been the Emeritus Professor of Ocean Engineering Department at IIT Madras. During his tenure, Professor Vendhan developed postgraduate courses in offshore structure dynamics and wave structure interactions, primarily using finite element method. Under his guidance, 12 of his students received PhD at IIT Madras. He worked on a few important projects for the ISRO and DRDO since 1981. He also helped the growth of NIOT, National Institute of Ocean Technology, since 2005. For his contribution, he received Academic Excellence Award by DRDO in 2011 and National Ocean Science and Technology Award in 2015. Two spatial issues, namely Journal of Engineering for the Maritime Environment, Volume 227 in 2013 by Sage Publications, and Ships and Offshore Structures in December 2015 by Taylor and Francis were brought out to mark his retirement. His research areas include offshore structural dynamics and finite element modeling of wave propagation problems. With this, may I request Professor C.P. Vendhan to say a few words about his association with the finite element method before we commence the presentation by Dr. Ghosh. Thank you, sir.
Thank you, Professor Dasgupta. I'll just say a few words by way of introduction, reminiscing my association with this topic. I joined the Ocean Engineering Department in 1980. In fact, Mr. Ghosh was a professor there. Maybe he doesn't remember me. I don't think I have met him formally. He was there for about 3 years, I guess. I'm basically a civil structural engineer when I joined the Ocean Engineering Department, with the emphasis on structural mechanics rather than design. Then our contact with the ship structures started when Mr. Paramanand, and I think many of you know him, Director General Naval Designs, he came to us early 80s and said that we want to redesign this ski jump structure of the INS Vikrant, that is the first Vikrant. Whatever we got from the British, he felt that it was too heavy. Why don't you do a finite element modeling and also an experiment? Professor E.D. Chandy made a scale model, and then he carried out experimental studies on that. And Professor Subrata Bhattacharya, many of you may be knowing, he is a naval architect basically. In fact, my naval architecture knowledge originates from my association with him. That is how I picked up ship structural particulars. So we both did a finite element model at the time. Obviously, it was our own code because there were no package programs in those days. And we came up with a suggestion that the original design given to us had too thick plating, and we wanted that to be reduced. We even went to the extent of saying it could be as low as 8 millimeters, because we quoted a British paper where he said that when an aircraft lands on the deck, and if it is as thin as 8 mm, some may develop permanent set. But then the suggestion was that you can simply cut open and re-weld a new plate and then continue to use it. In that sense, your ski jump will be lighter. Of course, the Navy did not accept that. So we gave our analysis results to them. And after that, I think they might have used it in their future missions. We also did a small project for Navy on plated mass, finite element modeling. So those are the two examples I would like to quote to show my association with the ship structural analysis. After that, of course, I've been doing a lot of finite element development, and as and when some structural analysis in relation to finite elements and other structures are there, we used to take them up as it is. So I'm really glad to be here, and it's very inspiring to see Mr. Ghosh after so many years, although I did not meet him formally, and he's there to talk about finite element modeling. So we look forward to his interesting talk. Thank you.
Thank you very much, Professor Vendhan. Thank you very much. It is my privilege and honor to introduce the presenter of today's webinar, Dr. M.K. Ghosh, who is an octogenarian, possibly going to be 90s soon, and whose energy and vigor is perhaps more than many heart. He is forever in the pursuit of knowledge, and I'm sure we shall have an excellent presentation from him. Dr. Ghosh as a member of India, he pursued and completed PhD in interest analysis from the Bombay University. His relentless pursuit of knowledge resulted in him writing and publishing 8 his training from Germany. He later got his ship survey and ship survey training from Newcastle. During his professional career in India, he occupied following positions. He was a chief ship surveyor, DG Shipping, chief general manager and senior professor and head of Naval Architecture Department of IIT Madras. Call for social responsibility weighed heavily on him, and he eventually switched over to environmental and other social sciences in the last 2 decades. He's authored books. I think we have a slide on his books. Amir, can I go to the next slide? Yeah, thank you. He started, his first book possibly was The Sea Ship and Seafaring. And then subsequently, he published many books, including Sustainable Development of Environment, Energy and Water Resources, Green World, Green Energy, A Search for New Way of Living, Renewable Energy, Water Resources, Strategy Overview of Global Sustain, Global Warming. Till recently, he was the president of NGO, Millennium Institute of Energy and Environment Management in Kolkata. He also acted as the chief editor of the journal Green Earth and Green Earth of the same NGO. INA has endowed him with Lifetime Achievement Award. Today's presentation, I think it would be nice if you can have the first part of the presentation by Dr. Ghosh Roy, giving the introduction of his presentation and the thought and the basic concept of finite element method.
After the introduction, how I bring the paper? They will bring the paper.
Have action the entire active. And go for it. Yeah, okay. Sir, Roy, you are on mute.
Hello.
Yeah, so yes, so
INA and President Dr. Manu Koirala.
Yeah.
I thank you
Thank you
for inviting me to talk on this subject, which is a pioneering subject in India at the moment. I thank Professor Vendhan and Jyotisman Dasgupta, who has revived the institution of naval architecture last 3 years, and now the onus is on Dr. Manu Koirala to take it higher and higher. I can say to Professor C.P. Vendhan that I was an invited professor of naval architecture and only professor at that time in 1980 by Professor Indiresh, directors at that time. I thank Dr. B.B.S. Iyengar, and all others who made this contribution possible for me to deliver. I now start my paper. Thank you.
Yes, Dr. Ghosh, you can go ahead. Yeah.
Yes. This transitioning, it means this is a new way to review, to design theory of ship structure. Even civil engineering, it is already well established, but naval architecture, it is not being taught, to my belief, to any other institutions at the moment. Ship structures are designed by the rules of the classification societies that Lloyd's register American Bureau of Shipping. The basis, theoretical basis, is the beam theory, where ship is treated as a one-dimensional structure. In finite element analysis, we discretize the ship into parts, so-called finite elements, and treat each elements and the loading by the sea and the shipping operation. And that's why we are calling it the transitioning to ship structure design by finite element analysis. This is the first part. This is the source of the book, which is published 3 months ago. It's very fresh that I'm presenting this paper. This part 1, I'll be helping you knowing the concept of ship FEA. Starting with the preamble here. Finite element analysis is a powerful method designing complex structures of frame, shell, or any large spirited vessels like ship subject to dynamical loads at sea. Application of finite element analysis in the design check of what component of ship structure is now made mandatory by the international classification societies for ships of 100 meters in length. Unfortunately, APA technologies are commended by 4 or 5 classification societies of eminence, and there are not many textbooks on the design of ships by APA. I'm speaking in a world. India, there is none. Application of APA is now predominantly restricted to civil engineering, structures and shells. Today, researchers and professors of APM has not sought so far APA application to ships. Naval architecture faculties should now sponsor courses and design of ship structure. Now that a textbook is available. Here. Yeah. This is the part of a deck plan of a ship. This is the after bulkhead. This is the forward bulkhead. This deck area has been discretized into rectangular elements. This is the finite elements. Defining ship finite elements. To apply finite element method to ship structure, we need to discretize the ship's plated body continuum into many finite elements as shown in figure 1.1. Those elements are assumed to be structurally connected only at their corners or nodes. This is the element, and this is a node 1, 2, 3, 4. These adjacent elements are connected only through the nodes. The sides are free. So this is how the element is treated. The loading and displacement are considered only at the nodes. In this discretized condition, stiffness of each node called stiffness coefficient in FEA technology of every finite element is derived. We will gradually develop method of deriving the stiffness coefficient. We are familiar with the beam theory in the strength of materials. The beam is a really one-dimensional finite element. Similarly, each small rectangular of the ship deck, as shown in figure 1.1, is a two-dimensional finite element. In the following section, finite elements are discussed in some detail. This is a beam. It's a load here, but normally loads are transferred to the nodes. So this is a node, is a moment load, M1, M2 moment loads. R1, R2 is a displacement, nodal displacement at the nodes. This is a node, this is a node, this is a single element. So displacement is R1, R2 and moment load M1, M2. And connectedly, we have stiffness coefficients termed K11, K12, K21, K22. This is the K11. This is K21. This is the stiffness. This is the load but force required to get unit displacement, here rotation. So here is a displacement here at node 1 and node 2, the displacement is the D2. This is R2 really. Beam element in this, with respect to the figure, I'm saying is shown a beam element loaded by beam N moments M1 and M2. I have shown and undergoing nodal rotation R1, R2. Then the nodal stiffness coefficients K1, K12, K21, K22 are defined as below. K11 is the load moment required at the beam end 1, beam end node 1 to rotate the same node by unit displacement. So this is the part stiffness at the node 1. And there is a additional load stiffness K12, the load experience and the beam end 1, while the other beam end undergoes unit displacement. This is as respective node 1. And node 2 similarly K22 is the load required at beam end 2 to enable the same end to undergo unit displacement. And K21 is the other part at the node 2, load experience and beam end 2, where the other end, node 1, undergoes unit displacement. So end rotation, this beam, end rotation, degree of rotation, freedom is called R1 and R2. This value is usually unknown or unknown. End moments is M1 and M2. This is load we know. Nodal stiffness we know, but we can derive and know. K11 and K12, K21, K22 will derive. I'll show you afterwards that they can be derived, and by derivation we know them. Degree of freedom 1 at node 1, and also node 2 is 1. This degree of rotation is the how many axes each node can take 6 displacements. So here I've got only the one moment, so 1 degree is there. Here also the M2, 1 degree of freedom. Nodal equilibrium equation beam element. So when you multiply the steepness with the R1, we got the load here. And the part 1 of the steepness and part 2 of the steepness. This is due to the rotation of the node 1, and this is due to the rotation at the node 2. This equilibrium equation we write in the matrix format here. This is stiffness matrix, displacement vector, load vector. As you know, in matrix treatment, this is the multiplication. This is a multiplication. This is also multiplication. So rho into R row and column, rows into column is this two. We'll proceed further. We have come to a plate now. We have shown you finite elements on the ship deck. The drawing, the first drawing we have shown. So 1, 2, and 3, and 4. So the 4 nodes are there. And this axis, we have got a positive, you can say positive load, rotation load, and same in the same direction, M2, the plate deflects. So this is a rectangular plate element. Other one is a beam element. The rectangular elements, we have got 4 nodes, 4 displacement, 4 moments. Each node is to be notified by the is a coordinate axis. X1, Y1, X2, Y2, X3, Y3, X4, Y4. Beam element, the beam effect, which you showed the beam element, K1, K1, 2, this line, 2. And because it is the plate element, effect of the second beam element, 3 and 4, this stiffness here is also affected in the beam element. Stiffness here is affected by the rotation and two, but in this case, the stiffness at 1 is affected by the rotation or displacement at 3 and 4. This is the difference between the beam element and plate elements. Here I am showing in a matrix form. If it was a 2 instead of a plate, 2 beam elements, this is the upper beam element, this is the lower beam element, and it is the because of the presence of the plate and stiffness has transferred from 3 and 4 also to the beam element 1. This is the effect of plate effect, and this is the beam effect. This is the beam effect, and this is the plate effect for each node. Here, I have the two photographs of bulk area, full of nodes. I can say rectangular nodes. All these rectangular nodes, but it not be rectangular. It's a quadrilateral, it can be, but rarely it's a triangular also. Here also the triangular nodes, I think it is there. This is an oil tanker, full of nodes, full of elements, finally definite elements, full of elements. Structural AP model of 3 holes and oil tanker. This is 3 hole, and these are all discretized into innumerable number of elements. Here also 3 consecutives. Normally preferred one compartment is this compartment is chosen normally. But you can also, there is an option, you can take the end compartment also, but then conditions differ. This is the same thing I have said. Now my part 1 is finished, and Vijay.
Thank you very
Just
much,
one
sir.
minute, Vijay. Yeah. I have to go back. Part 1 is finished.
Yeah.
Okay.
Okay.
Part 1. No, this is anyway.
Thank you
part
very
one is
much, sir.
finished. I will
You
part
wanted
2.
interactions?
Is there? You cannot. We cannot go back to the screen.
Yeah, we can.
Stop. So, Mr. Dasgupta, is there
Yes, sir.
any
Thank
queries?
you.
Then I'll talk.
Okay. May I request any of the participants in the audience, if you have any comment, you can raise those comments, and may I request Amir to take those comments
Sure, sir.
and bring them
We
on
have
board.
2 raised hands, sir. Right now, I don't see any comments, but we have. So I will add
Yes.
Gobind Sinha,
Okay.
Mr. Gobind Sinha, to
Okay.
the, if that is okay with your
Yeah,
permission.
yeah, Dr. Govinda Sinha. Yes.
What is the comment?
Hi,
Yes, Dr.
can you hear me?
Govinda Shin. What are the comments?
Yeah, we can hear you.
Hi, sir. Let me thank you that you
In
have taken
short,
your.
very short.
Yeah, just to tell you that one, the finite element analysis of ship structure, from the classification point of view, it is almost mandatory, which is the 3D cargo hold analysis.
Okay,
And
thank
for
you.
the
Thank you. That is enough.
and just to
Any
tell you
other
one
any
thing,
other comments?
currently
No. I have heard you. It is accepted.
and
Only
another
no
is
rejoinder.
your
No rejoinder.
three,
Short.
three, three, and three cargo hold. What you are telling is the one cargo hold. Actually, you have to model the three cargo hold. This is mandatory to assess the middle hold. And
Hey,
you have to shift the
yeah.
3D cargo hold models along the length of the vessel to assess the
Okay.
0.4 L, So that
Thank you.
procedure is established.
Going to
Yeah. Thank you, Dr. Sinha.
uh,
Can I request anybody else? Any other is
no,
raised?
I'll proceed to
Amir?
Yeah, we have Mr. Apurbakar also raising his hand. Mr. Apurbakar, if you want to ask your query here. Thank you.
That's the mouse.
Hello.
okay.
Yeah, yeah.
We have got part
Yes.
2.
Yes, sir.
Part
Ca-
2 is the primary ship
Okay,
finite
we'll-
element. We will
Yeah.
show.
Okay. Yeah, Mr. Kaur
We have,
and Dr. Sinha,
we
we
have
can.
just. I'm talking now. Give the lectures. No
Yeah,
further
yeah.
question.
Please go ahead, sir. Yeah, please go ahead. Please go
Yeah,
ahead.
yeah. This is the ship sections. A simple model I have made here. Deck, bottom, ship side, ship side. We have discretized in 45 finite elements. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. And like that, it is going. And nodes, one node, 1, 2, 5, 6. This is a node. This is the element 4. Element 4 has 5, 6, 9, 10. Another element. And 4 nodes here. Vijay. Vijay. It's not going to the next. Next node is
Next slide. Yeah.
just 1 minute.
Yeah.
Oh, stop.
No.
Stop sharing is. Okay. No, it's not going. Okay. I'll directly do it. Huh?
Yeah.
No. Not. So the same ship sections, a rectangular finite elements 45, deck assembly 16 nodes, two sides 32 nodes, ship bottom 28 nodes. Some of the nodes are common. We leave that 60 nodes. So this is a element 4. This is the element 4. This is the element 4 we'll be talking about of this section. So this element 4 is got 4 nodes, 5, 6, 9, 10. This is called the global degree of freedom. This global degree of freedom is only serially, but we have also, for calculations of the node itself, we have local axis called a local DOF 1, 2, 3, 4, 5, 6, 7, 8. So here in a matrix form, this is the global degree of freedom, 8 degree of freedom. Each node has 2 displacements. This is a 2 DOF per node. So total 8 nodes, which is indicated by the local DOF 1, 2, 3, 4, 5, 6, 7, 8. So here you can see that each stiffness is contributed from each node. And for each DOF. So node 1 influenced by displacement of 1, node 1 influenced by displacement at node 2, then 3, 4, 5, 6, 8. So this is the node 1 contributed by the stiffness due to the displacement of node 8, DOF 8. So whole this 8 by 8 matrix represents the stiffness of element 4, K4. Element 4, this is element 4, its stiffness is K4. And each point, there is a 8 part of the stiffness. Now in these discussions, we have got several functions, but it's very important that here in this page, we are discussing displacement function N. Then we will have a displacement function B. And stiffness coefficient are already introduced K. So N, B, and K are very important functions in the analysis of the finite elements. So here displacement inside the element in terms of the nodal displacements. Nodals, we have now recognized the nodes, the corners. So corner displacements, 4 corner displacements in this case, and is a function N, displacement functions. So we can determine the displacement at any point if we know the displacement function, also called the shape functions, and it is the nodal displacements. So since it's because of 8 degrees of freedom, the element displacement of a 4-node element can be represented with 8 constants. So here, displacement U in the x direction, V in the y directions of cartridges. So this is represented, this is because of 8 degrees of freedom, 8 constants can be used. These are constants, alpha 1, alpha 2, alpha 3, alpha 4. So UB, so hello. So U displacements, this multiplied by this is line, this line. This row multiplied by the column or U, which is alpha 1, X alpha 2, represented in the normal fashion, algebra fashion, and this is a metric fashion. Now, from there, we have showed this one. There's a displacement. 1 second. This is a nodal displacement. Displacement at node 1, node 2, node 3, node 4. Since we have got node 1, we have the properties of the node 1 here, x1, y1, x1, y1. This is the connection matrix, it's called. So U2, this connection matrix is this. So if you divide this inverse, note inversion of matrix of equation 6.2, you can -1, it is the inverse of this matrix. So if you multiply this inverse matrix with this side and this side, the multiplication of this is 1, this is alpha 1. So alpha 1, alpha 2, 3, and 4 equal to inverse of this matrix, correction matrix, and nodal displacement. So the total things, we have internal displacement inside the element, correction matrix here, and instead of alpha 1, alpha 2, we are writing this part. So UB connection matrix, this is the inverse matrix A -1, so inverse, and this is the nodal displacement. Now, this is also equivalent to NA, which we have shown the first figure. Our displacement function N is defined as the shape function or displacement functions. If we know N, we can straight away get the displacements from the nodal displacement. This is just a way of writing N1 functions N1 x1, N2 x2, N3 x2. This we write because we have put in same line column x displacement, x direction displacement, and V is the y direction displacement. So U is N1 ion, N2 is the U2 leaving, this is a 0. So this is a way of this. This is, I'm coming to the next function, there is a strain displacement function B. This is a strain function B. Ex epsilon x is the strain in the x direction, epsilon y in the y direction, and this is the shear strain xy plane. So sorry. Hey, বিজয় পেছনে পেছনে যেতে পারছি না।
আপ করবে না?
হ্যাঁ।
আপ অ্যারো। হ্যাঁ।
Here you can see that in this matrix equation, eta x, the strain is defined by derivative of displacement u. Strain y, derivation of v in the y direction. xy, this is the shear strain expression. So this is what is shown here. This is u is the here is shown u equal to n1 displacement function coordinate. So the derivative of u is derivative of n1, n2, n3, n4. Derivative, this is the strain, and derivative of n1, n2, n3, n4. The zero is only for positions because the column constitutes of u and b. That the first line b is 0 and second line u is 0, and shear strain is neither required. So this whole matrix is called the B matrix, strain matrix. So epsilon, this is column epsilon, and this is a B matrix, and it is the nodal displacement. So from there we got the strain. This is a strain, is a B matrix A1. Your sigma is the stress. Sigma is obtained from the strain by applying to modulus. For unit modulus, we know E, we know gamma for shear strain, but here plane stays, two-axis plane, we have got a D matrix for the as a constitutive element, it is called. So stress is in terms of the E. So E is again B E. So B E. This is the D, is the constitutive matrix. It is like a Young's modulus or shear strain modulus. So we have একে দেখো না we have finished the part 2. Any clarification needed? We go back to the part 2 we have cleared, and we go back to this original. Anyone else for clarification? You don't have to restart, then just sit.
So I would suggest that you go through the part and the stress and strain from the matrix. So, which is very well appreciated. You please go ahead with part 3, sir.
Okay, thank you.
We
I
shall
will,
have a
go to
combined
part-
interaction at the
Okay.
end of.
Part 3.
Thank you, sir.
Part 3. Okay. So it is a hard analysis. We did the primary analysis. You know, element is a rectangle. It is very easy to do, comparatively easier. But if the element is a quadrilateral or other shapes, we have to convert it.
Which slide is it?
Huh?
Which slide?
Yeah.
Yeah.
Yeah. Okay. This is a quadrilateral. In the figure, a quadrilateral finite element in physical coordinates xy. This is x1, y1, x2, y2, x3, y3, x4, y4. This is a natural coordinates. Always rectangular. This is a shape. 1, 2, 3, 4, and its coordinates is -1, 1, -1, 1, 2. This is 1, 1. So this is a R and S coordinates. So R is -1 here, 1 here, and S is 1 here, minus here. So in the figure, a quadrilateral finite element is physical coordinates xy is changed to a so-called linear isoparametric finite element in natural coordinates. So why it is called isoparametric? Because though it is a quadrilateral and this is a rectangle, the displacement function n is common. We'll just go to next slide. Isoparametric elements. N is the same, but N is expressed in R and S coordinates, natural coordinates, and X and Y is a physical coordinates. And here also the displacement can be, this is N1, the displacement, vertical displacement, this one. So, but this B matrix and strain, they're all XY coordinates. So we have to bring all of them to RS coordinates. Next slide. Please listen to this. The analysis of isoparametric finite element. Physical model element is expressed. What is this? Covering. Can it be removed? XY, while the isoparametric element is natural RSS, while it will be shown that the shape functions are expressed in natural coordinates, RSS coordinates, the strain displacement matrix is B is expressed in X1 coordinates, and therefore thereafter converted into RS coordinates through the application of Jacobian matrix. Hence, we will briefly discuss the Jacobian and their matrix here. Now, the relationship between the two partial derivatives of two systems. This is a Jacobian derivative with respect to R, derivative with respect to X. This is called this conversion factor del X by del R. It is the J. J is the Jacobian in one direction. If you have two dimensions, R and S, here only R, X. But actually the rectangular elements and elements are in R and S. So in natural coordinates, local coordinates is called sometimes. And this is Cartesian coordinates X and Y. And this is the Jacobian, two-dimensional Jacobian. So this is the way we convert all X coordinates into R and local coordinates R and S. Here, this is briefly written G1 and del R, del S, del X, del Y. But we want to convert B matrix, which is in Cartesian coordinates. So B matrix is written here, X and Y, to convert it into R and S. This is a requirement. For that, D and X comes here, del R comes here, and it is inverted. This matrix is inverted. So inverted matrix is defined here. I would not go into details. This is the divided by determinant, and this is the way to convert it. We did not go here just now. So here you see there a shape function xy naturally is given by inversion. This expression in the derivatives in the x and y and a derivative r and x. This is the Jacobian matrix. Here, this we missed out. The J is the Cartesian coordinates for this special rectangle, which for simplification we have used, or origin is 0, 0, or opposite 2A, 2B. It is special, made simple to get a simple value of J. So this rectangle is converted to the natural rectangle by this J, and inversion of J is this. So the inversion of J is here, we converted here. So this is multiplied, we get B, which is in Cartesian coordinates, into RS coordinates. All ordinates here, coordinates are all R and S. So values in N in R and S is given and before, they are converted to R and S value. Here, this is the displacement functions. This value is given R only in natural coordinates. This is the natural coordinates. So Cartesian coordinates B has been converted to B in RSS coordinates here. Then it is simple to derive further. So we will stop here, but we go to uniform load. We have talked with the ship fine elements, but we have not talked with the load. The load in each element. This is a physical element. Load is in various shapes here, but we have to convert it into the nodal loads. This four corner, whatever is this, is a vertical lateral force or horizontal force, horizontal X, horizontal Y. Two examples we are getting: uniform lateral load vector or Q on a rectangular element. So if Q, what is the load in the nodes? Here DRS, NT, we know the value, and Q and O, 0. And this is the determinant of Jacobian value. This is the formula which is derived. We'll show it further, this derivation. We get from Q, value get N1, N2, N3, N4. Lateral loads at right angle to the plane of the element. This is the uniform lateral loads. And this double integration has to be done by numerical integration, Ghosh quadrature. It cannot be done straight away. So this N1, N2, N3, N4 is integrated naturally, numerically. Yes, these 4 points, R1, R2, R3, R4, this values of these four, N1 value, N2 value, N3, added for only R1. Then we got the N2, N3, N4, same, because the uniform load. We got the Q1, Q2, Q4 loads for 4 nodes. We have the value ABG. ABG is all the size of the element, and Q is the uniform load. So it is just simple. It is shown that how to do it, but actually without doing, but if the rectangle is uniform loads, it is a 1/4 area. This is 1/4 area, AB and Q. This is the pressure. Uniform load is a pressure. Body force. Body force is a gravity, is a body force. Here DRS, NT, FB, thickness. It is Jacobian determinant. Here NT, FB is downward gravity, and it is the displacement functions. N1 shape functions. Here it is working not a displacement functions. Here it is shape functions. It both received. So from here we get the coordinates here multiplying. Then numerical integration. This is the numerical integration at 4 points we integrate. So this is only integration N1 we are integrating. So 3 other shape functions N2, N3, N4. The same value you will get. And finally, body force also, it is a constant tab 1/4 the value, tab RG, tab RG, tab RG, tab RG. Is a minus is a negative direction, downward. This is one page I missed. How to determine stiffness coefficient. We have developed derivations of N. We have developed derivation of B, N shape function, discrete functions, and B is the strain function. But stiffness coefficient we have not. And so load function also we have not. That's a little difficulty. I said I'll do later. So by application of virtual work means in a strained body, if it undergoes small displacement, then the internal work done equal to the external work done. Here internal work done strain into stress, sigma. So transpose T is shown. That is how this is a matrix process. T is required. This is a horizontal and it is a vertical matrix. So external work is a force into small displacement is a external virtual work. So this is the body force. This is the surface force. This is the isolated force, surface force, body force. So this ultimately we get this line. We have shown you that develop the NT-FB, NT-DS, and API. API I have now shown these 2 examples I've just shown you. And left-hand side is the stiffness matrix. Is also quite complicated, requires numerical integrations. Strain matrix transpose, D matrix modulus, constitutive modulus, and B matrix. So integral equation, integral of this you got to KU. And log vector elements from here, NTB, I just shown you this. So this gives the K. So all the important functions we got K and B. Well, this is the last part. The plate used in ship has got a stiffness. So it can be bent we have planar stress, here is bending stress, flexure stress. So this is a plate 1, 2, 3, 4 bendable plate. So at each node in a plate, it was a lateral deflection W, and theta x is the rotation x1 and rotation y1. That means this point goes up and down W, then the theta x is the rotation here, and theta y is the rotation here. But a little difference is there. Theta x is dw dy. This is the deflection in this direction. And this is the deflection in the vertical direction, this part. So this x axis bend like this, all this. So isometric property, to do the plate elements, we have to use isometric properties of plate elements. We have shown the functions before. X is this is the nodal coordinates, and any other coordinates in terms of the 4 nodal coordinates, 1 to 4, 4 nodal coordinates. Y also, Y in the inside the plate, this is the nodal displacement, XY plane, and this is a lateral deflection. This corner just up and down. And this is the rotation, X directions, rotation Y directions. So dw dx is the rotation Y with Y here, double derivatives, n derive Y, single, double. So bendable plate, curvature functions, Cu ux, Cuy, Cuxy is a shear curvature. Shape functions, this is known to you from here. I've several times used it. Constitutive material CM. We have used D. Here we are using C because the bendable plate is its form is this. So when you have a plate, we have rotations, flexure rotations. But classification also today required that shear strain has to be taken into account. So if the full deflection of the plate is theta y or theta x, it is divided at, this is the flexure part and this is the shear part. This is the total deflection, flexure part dw dy, and this is the shear part. Now shear strain is phi y. it now constitutes of flexures and no, sorry, this is the total part. This is the shear. This is the shear part, flexure part, and total deflections. Phi y strain, shear strain is a flexure strain and total deflection. So for epsilon is a strain, as you you that for paper non-strip, epsilon has three parts: epsilon x, epsilon y, epsilon xy. Here, these three is there, plus phi x shear strain and shear strain y. So this is not plane, this is a plate. So components at each node, vertical deflection, theta x rotation, theta y rotation, and phi x and phi y are converted again into this strain. I just next slide. This is the rotation theta y. Sorry. This is the theta y represents this multiplied this. This is the theta x multiply this rotation in the y directions. This is a shear. This is converted from shear strain to in terms of the displacement functions. So we don't have to represent independently. This is this multiplied by W1 and NY theta y. It will get the shear, both of the shear strain expressed in this one. Using the isometric properties, we have converted from shear strain to displacement functions you can use. This displacement functions, shear. So this is a two-part flexure strain. B is a strain function, but this is a flexure, this is the shear. We have got further elaboration of this that we don't present it here, excepting this. This is the flexure part. This is a flexure part, shear part. This is the constituent CP, plate constituent CP, and this is a flexure, this is a shear strain. This is two parts, and K per stiffness, K is stiffness due to flexure, is stiffness due to shear. We have not gone beyond it because you can really very elaborate calculations. We can do on a computer only. But simple one, we have done in the book, it is shown, it is done without computer. So the last part, ship. These are the processes relevant to ship's analysis. We have seen in 3 parts. We have dealt with ships, but the processes as applicable to the ship we have shown in part 1, part 2, part 3. Drawing the ship finite element, then primary ship finite elements analysis, then part 3, isoparametric analysis as applicable to ship. Here, a ship's plate, transverse stiffener, longitudinal stiffeners. We have taken an element from here. 1, 2, diagram is not very good. 3, 4, 1, 2, 3, 4. This is a stiffener. So plate elements 1, 2, 3, 4, 1, 2, 3, 4, angular stiffness 3, 4, 3, 4, and plate DOF. Plate DOF, 3 flexures, 2 shear, 5. Total, you have got a 20 DOF. Here, 3 stages stiffness solution of a real ship hull element. Composite stiffness of the ship hull element consists of not a first stage solution, planar stage membrane 8, UV. Planar membrane is UV. Second stage solution, bendable plate 12, 3. W, theta x, theta y. Each element is W, theta x, theta y. And stiffening member, it has 8 DOF. That means at node 3 and 4, we have got lateral deflections, axial displacement. Beam can axially elongate or contract. U. Lateral deflections, which you usually beam vertical deflections. And bending, EX, if in natural beams, your lateral deflection and you have a curvature, dW, dy. Shape, not curvature, curvature is a second degree, EY, dW, dx. So some of them are common. So instead of 8, 12, and 8, 28, we get 20. For beam, you can apply the strength of materials. So complicated calculation is not needed. This is the axial force. This is the W vertical force. This is the bending. This is the ZZ is the torsion. This is the torsion. Torsion, theta x. Theta x is the torsion, theta x. And this is the bending slope. From there, for beam, we got this stiffness matrix, this total, which I have shown in the diagram. If you convert it to the stiffness matrix, this is the stiffness matrix. These are all well known to us, EAL 12 for vertical these things, bending this. This is a torsion. This is also again bending. I'm not going to details. This he dove in strength of materials or slope theory. This is the for the whole plate element. We have got, I said, 20 degree of freedom, DOF 20. Matrix is 20 by 20. Yes, I don't have place, so it's a 10 and 11, 11 to 20. So 20 by 20. I'm showing this as thickness format. So far, we have talked of the elements only, finite elements. That means we broke the ship's continuum into numerous elements and treated them. Load versus stiffness. Now, at one stage, we have to bring back the elements, assemble them, discrete conditions. So, this ship section I showed you before, as a simple example, this is element 4, element 4, element 1, element 4, and vertical is not missed out, 13 element 13, but nodes are there, 1, 2. So this element 13 at node 1 and 2, it connected to the element 1. So this way. And element 4 is connected to 1, 2, 6. So we have to collect them and write down the stiffness matrix for the whole structures. For a ship, it will be quite a lot. Hundreds of 600 to 600 minimum. More. This is the 13. Each has the three elements. This is the element 1, element 4. These three, if it is joined like this, assembly, the stiffness element will be this way. You see, it says 12 by each element 13 is 12 by 12 elements. No, 12 by 12 elements. Then this is the one, element 1 and element 4. We have to match ships 1 and 2, and this element 1 and 2 here. But it gets shifted because of the two other elements shifted. And again, this is 5 and 6 common, 5 and 6. Element 1 and element 4 common is 5 and 6. So this is the. So these three elements have been assembled. This is the way. So there is Mr. Dr. Govinda Sinha has says something about classification. Classification rules is not the aim of the paper. We are finite element analysis science we are talking about. But however, oh sorry, hey Bia, সরে গেছে, স্টপ সরে গেছে।
স্টপ শেয়ার করেছো?
হ্যাঁ, না, 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 আমি উল্টো টিপেছি। Bring back, how to bring back? So stop. Share.
নাও अगेन শেয়ার।
Huh?
শেয়ার করো, ওটা ছাড়ো।
Share.
হ্যাঁ, এটা তো
এটা তো নাম্বার 1। ওকে।
গো স্ক্রল ডাউন।
Oh no, stop. আচ্ছা,
কোনটাতে যাবে?
হ্যাঁ,
কোনটা?
লাস্ট অনেকটা সরো দেখো না, চলে যাবো না, এখানে এই যে লাস্টে। একটু রান করে না তো হবে তো?
করো।
স্টপ শেয়ার না?
কেন স্টপ শেয়ার?
Yeah.
হ্যাঁ,
Can you see it now?
Yes,
Oh,
sir. We can see it. Yeah. You can go to the next slide, sir.
Yeah.
Please.
আচ্ছা।
Yeah. How many more slides, sir? How many
Sorry,
more
but-
slides?
How to do? Anyway, this is the process
Okay. Yeah.
common to the classification society. Sea loads, ship loads, choosing the cargo holds. These 3 cargo holds we have chosen. Structural model formulation, sea load, boundary conditions, ship operating loading. Finite element analysis. Finite element analysis, after the finite element analysis, we have to get in the design format, the yield strength. You see, if you stress in one direction, it does not give. We have to, at this point, total strength is the yield strength sigma 1, sigma 2, sigma 3. Then buckling assessment. And then high stress areas where stress concentration is there, opening and all. Then hotspot areas, welding spot, welding joints and all up and down for few millimeters. You got a hotspot stress, and at that space is the vibration is there, fatigue strength is affected. So this is the overall background of the application of finite element analysis of the ship. Of course, in compliance with the classification society rules, they are the approving authority. But this paper and the book is for institutions. It is not yet for the commercial, the developing commercial software. That work is yet to be done. It is for the institutions I have made single-handedly. Old man, naturally, everything cannot be tried, but basic science of finite element analysis I have given in the book, and one should read the book to understand. In one presentation, I appreciate that you can have only glimpse of it, but we cannot do the work by the projections. Okay.
Thank you, sir. Thank you very much.
Thank you very much.
Thank you very much. You have virtually covered.
Stop.
Ah,
Stop. Stop.
Sharing.
Then.
Yeah.
Yeah.
Okay.
Ah.
So you have virtually covered the entire mathematics and physics of this solver, finite element method solver,
Ah.
which is the crux of the entire finite element method.
Ah.
You have covered the finite element matrix solution, mathematical formulation and theory. You have covered the shape function concept, covered the Jacobian matrix and matrix inversion, strain matrix, and many of the other aspects of the finite element solver. So with that, I congratulate you, sir, for having made this book the theoretical foundation of the finite element method. In the commercial domain, the finite element method has application in many areas, and it has progressed quite a lot. So I would think that it is time for us. Am I audible to everyone?
Yes, audible
Yes.
to me.
Thank you, sir. On the basis of your presentation, and there are very important aspects on the pre and post processors, the load matrix application, and then the final stress values and what can be accepted. With that, sir, I would request any questions which may have come to mind of, or any comments from any of the practitioners of the finite element method in SHIP. Before we go to that, I think it is necessary for me to highlight that while finite element method is being used here, most of the softwares which are being used in India, they are all overseas software. Of course, there are Indian solvers available, but the full package of finite element method application for shipboard, we are all using the overseas software packages. So in keeping that in mind, this is going to be, one of the foundations on the basis of which India can, or our professionals can develop the finite element packages for full ship analysis to comply with all the regulatory requirements. With that, I would request any questions and question answer sessions. Unfortunately, we may not have too much of time, but at the same time, some questions can come. Yes, sir. Any queries on the methods?
Rajiv Sharma.
Yeah. Can we take Professor Sharma on the panel?
Yes, sir. Professor Rai Sharma is on the panel. Sir, you can unmute yourself and go ahead with the question.
Yes, Professor Sharma, thank you.
Can you hear me?
Yes, we can hear you.
Sir, thanks for a very detailed presentation, especially on the formulation side. I have one question. When it comes to large deformation, what is their role in the stability of finite element solution, sir?
Okay, can I?
Yes, please.
Yes, sir, please.
Yeah, stability is a deflection. High deflection is the sign of stability, instability. So if there is some work, but not much work, is theoretical for stability. Well, in the axial stress distribution, the element is dx. In stability, we start with ds. The ds means length of the element is x, but when you bend it, it is increases. And from there, the stability consciousness comes. So if in the finite element analysis, earlier stage, before refinement, if we see somewhere that the displacement is too much, you introduce in the next networking an additional node so that you determine the displacement what is there. So basically the 4-node element we use in a ship. If in a node, in a element, we see the deflection is high, we put additional node, so the displacement we find y. And you can repeat it and locate the deflected areas. This is shortly what I would present.
Yeah, I think,
Thank you, sir.
thank you. Anybody else would like to comment on this? In case it is related to stability of the solution? Okay. Any other question? Any other question? Yeah, Mr. Karan Doshi, yes, please.
Yes.
Yes, sir. Am I audible, sir?
Yes, please. Yes, please.
Yeah. Regarding the question by Professor Sharma, here the stability does not come into account because we are using a direct sparse solver. So it's a solution of linear equations,
Yes.
and there are proven algorithms for this. The stability
Slowly. A little
please
short
go.
of hearing.
Yeah.
Yeah, the stability does come into play when you are using a non-linear solution. For example, if you are doing a non-linear elastoplastic analysis.
Karan, can you just go a little slow,
Oh, sorry,
please?
sir. Sorry.
Speak slowly, please.
Yeah, I followed.
Yeah,
I don't have to say.
Yeah. Go ahead.
Basically, the finite element analysis we do mostly linear. The 4-node element you use, it was U equal to N1 x plus N2 x y N2 x1. This linear relation. So non-linear, because we are breaking it. Why should you bother now non-linear? When we are into breaking it into a small element, aim is to obtain linear relation. It is one node to other node in an element is a linear relations. Okay, thank you.
Thank you. Thank you, sir. Yes, Karan. Thank you. Thank you. Anybody else?
Thank you, sir.
Thank you. I guess, Professor Vendhan, would you like to make any comments, sir?
I think Professor Vendhan is on mute right now, sir.
Yeah. Professor Vendhan, you are on mute, sir. You got to unmute yours. Yeah, thank you.
Can you hear me? Yeah, okay.
Yes, we can.
To whatever he has described, he adds the
difficult
appropriate geometry stiffness matrix.
Yes.
The first step is he can perform a linear buckling analysis.
Yes.
Then you can add on to that and then do a nonlinear analysis. So these are the extensions one can think of, so that you can find out buckling of the plate panels or side shells or bulkheads, all that will come out of that. Provided these elements are added, these components are added to the element formation. That's all I want to. But I also wanted to make one observation. In fact, I wanted to do it right in the beginning.
This
When I
part
first
can I
learned,
answer first? This part
yeah, please.
I can answer a deflections you said by introducing additional node. What was curvature? We converted it linear two parts. Even into two elements also introduced, in the realization. So basically what classification society and all, as much as I know, they all are dealing with a linear element, is a linear phenomenon.
Yes, sir. Professor Vendhan, you wanted to say something else.
Just
something
only
more-
one
yeah.
observation.
Yes, sir. Please
When
go
I
ahead.
first learned about ship structural analysis,
Yes.
I read through the Comstock book. Maybe there is one more author than that. And I was really surprised to read the way he has broken down the structural behavior of a ship. This is something not often done in civil engineering practice. We don't do that. They're talking about a primary, secondary, tertiary, and so on. So whosoever uses finite element analysis of ships should go back and then use those basic concepts and then do a successful finite element model. This is simply going for a huge mesh without knowing what is really modeled. That's what I want to observe. Thank you.
Thank you. Okay, anybody else? Any other comment? Okay. With that, I think I have given my impression of the presentation today, and we, on behalf of Institution Naval Architects, we are immensely thankful to both Dr. Ghosh as well as Professor Vendhan for honoring us by being present in this webinar today. We are extremely thankful to you, sir. The things which Dr. Ghosh has covered, I think I personally learned this aspect almost 30 years ago, and there used to be one very interesting book called R.D. Cook, Robert Cook's book on finite element method. So that was, but that did not cover it in so much of detail, and not for the application on ship structures. So we used to call it Cook's book. So it was very interesting that way. In any case, thank you very much, sir. Thank you very much. You remain an inspiration to all the naval architects and professionals in the maritime industry. And with that, I would hand it back to Dr. VBS Iyengar for making the concluding remarks. Thank you.
Thank you, sir. It was a privilege to have listened to the talk by Professor Ghosh, as well as very insightful comments from Professor Vendhan, Mr. Dasgupta, as well as Mr. Gobind Sinha, Mr. Kar, Professor Rajesh Sharma, Mr. Karan Joshi. All of them participated very actively in the chat boxes, as well as not only what they said, but also there were very insightful comments in the chat boxes also about how the classification societies are using and where the classification societies and ISES is using these techniques with respect to FEA, with respect to the practical ship applications. Thank you, sir. And now I'll formally move on to the vote of thanks. My first vote of thanks is to the chief guest, Professor Vendhan, because once the talk was decided that it is going to be by Professor Ghosh, then we had to also have an appropriate person as chief guest, and one name which occurred to me was Professor Vendhan because of experience. So thank you, sir. Thank you, sir, for accepting our invitation and being the chief guest today. And as it's customary, I'll just go with the session chair before thanking Professor Ghosh.
Thank you, all of you, giving me a chance
Yes.
to present it.
Yes.
My idea is that spread the latest knowledge to fellow naval architects and enrich the profession. That is, at this age, I have ventured because one of the naval architects has once asked that can a naval architect write a book on finite element analysis? All the books are written by civil engineers, so civil engineer emphasis, which is not understood by us. We never liked it. Then I tried volunteers, others, which was not available to me. Then I proceeded to write these books. Over 3 years, I produced these books. Thank you very much.
Thank you, sir.
Thank you.
My thanks to Mr. Dasgupta. Actually, Mr. Dasgupta messaged this idea 1 month back or so. Then immediately I messaged Professor Ghosh. So thanks, sir, both for chairing the session as well as connecting me to Professor Ghosh for making this happen. And Professor Ghosh remains an inspiration for all of us. And being probably not only the senior most naval architect, probably I think he's the senior most practicing engineer in India, if I cannot be too much wrong. So with this, I mean, at this age and bringing out the entire knowledge as to not, I mean, FEA has been used, but as a textbook to be made available to Indian students. So very commendable. So thank you, sir. Thank you for bringing out the book as well as giving today's talk. Here, even you are an inspiration. I mean, that's the one thing you can tell. And my thanks also, as I thank all the participants. Today the attendance was very high. Around 50 participants joined for the lecture. And at least 2 or 3 of them were just single user, but we know that they were in their classrooms and listening. So I'm sure all those budding naval architects would be heavily enriched by this talk. They were listening in a classroom, so they will not be counting as one user, but essentially it is 30 people sitting in a classroom from IMU and IIT Delhi, as well as I'm in IIT Delhi, and so I'm very unCUSAT. Dr. Ebenezer was constantly messaging me from CUSAT, so I'm very happy that the young naval architects are able to listen to this and they'll immensely benefit from it. Thanks all the audience, 50 people. It's a very, very high audience. So thanks for all of us for joining. And with that, and thanking all, have a great weekend. And thank you. We can end the session.
Thank you. Thank you. Thank you very much.